so some specifics then for iterative PET reconstruction. I'll talk you through MLEM, which is the core of most PET reconstruction methods iteratively, and then talk you through in more detail an implementation of a MapEM method. So this was just a quick review of what I've already covered, and so I'm just showing this to you for just an accelerated version here. Remember, we started out with the Poisson log likelihood at the top there, and we took the gradient and we figured out that we could calculate the gradient of the Poisson log likelihood for any given candidate image. So whatever our guess is at any given moment is xk. You just forward project it, ratio back project minus the sensitivity image, and that is the gradient of the Poisson log likelihood. And then because we're maximizing the Poisson log likelihood, we just need to add on that gradient. For MLEM, there is a statistical derivation based on complete data, and I'd love to take you through that, but we need to be rather short and brief, and so I'm giving you this rather blunt approach of just putting this multiplicative modification in front of the gradient. And by doing that, that's how we end up with this EM update, which is very simple to understand. Given a current image, you forward model it with your acquisition model. And notice here I've also included the scatter and randoms background there. So once you've done the forward projection, sorry, just to be clear here, current estimate of the 3D image is xjk, which I'm showing here. Forward project here, add on the scatter and randoms background. You do the ratio here. So I'm just trying to get back into sync. There we go, ratio between the measured data and the forward model. And then of course here, this is the transpose or the adjoint of the system model, because we're summing over the first index. When we're forward modeling, notice we're summing over the second index of that AIJ. So this is the transpose of the adjoint, back projection if you like. And then we just can multiply this back projection of effectively ratio correction factors is how you can crudely view this with a normalization by the sensitivity image. We can just multiplicatively update the image to get the next update. So it's a very simple method, very robust actually, it has to be said, subject to avoiding division by zeros. And in fact, it's worth saying here that adding on a scatter and randoms background can really rescue you from some awkward moments here if your forward model is delivering zeros. It's very convenient to have a non-zero scatter and randoms background. Okay, this is what it would look like in a very simplistic implementation for a Shep-Logan phantom. So we're imagining that's the true PET tracer distribution using a Shep-Logan phantom. This is, if you like, the noise-free measured sinogram here. Forgive the change of notation to theta here. It's just like X. And here we've got our initial estimate. Now with MLEM, this is a multiplicative algorithm. So with the least squares methods, you can get away with zero initial estimates because you can add and subtract. MLEM, purely multiplicative, you can't start with zeros. So this is a non-zero uniform starting image that we use for MLEM. And then as we know, the first step is to forward project that. So here, this is a forward projection of my uniform activity distribution here. So forgive the change of notation. This is just a forward model is equal to the system model times X, if you like. This is XK in previous notation. And then what we're doing, as we know, based on the gradient of the Poisson log likelihood, is that we need to use the ratio of the measured to the model of the mean. That's what I'm showing on the top right corner there. And then we need to apply the adjoint of the system model. That corresponds to back projection, so A transpose of that ratio. So that's what I'm showing here. And then we divide it by A transpose 1, it's just back projection of unit data, and then multiply. And so that's how we get the first update of MLEM, a very simplistic method. So if you carry that on, progressively, this image will get closer and closer. This gets closer to that. And by 40 iterations, you can see we're getting, reasonably close to that true distribution. So a very straightforward method. Just to add further that the drawback with this is that you'll see in the forward model, we have to forward model into the entirety of the data. Now in 2D, that's fine, but in 3D, you're typically dealing with approaching 1,000 sinograms, and that can be slow, although these days, even forward projection into 1,000 sinograms is pretty quick. But because it's often viewed as being slow, what we do instead of forward projecting into the entirety of the data, we forward project into just a subset of the data. And so I'll show you that graphically just as a snapshot, what that would look like. This is, first of all, the algorithm, though. This is Hudson and Lark in 1994. And the key difference here is really, this is identical to the previous MLEM algorithm, except that now we're back projecting only over a subset of the sinogram bins. And I'll show you that graphically in a moment. And likewise, the sensitivity image now also needs to be just over that subset for a particular update. And so that means whilst this forward projection looks like it's doing a full forward model, I should have a +B here. In reality, you only need to forward project, of course, into the subset that you're about to back project. There's no point forward projecting into data that won't be used. And so in other words, if you use 10 subsets, 16 subsets or whatever, that's an order of magnitude less work to do a forward projection and a back projection, and you've already got a multiplicative update. So this feeds forward into these kind of stochastic based approaches where, even like stochastic gradient descent in deep learning methods, where you're only using a subset of the data to do an update of your parameters. So that's the analogy for what we're doing in OSEM. This is what a snapshot of it would look like. So there's the ground truth image again. This is an example after doing only, now we talk about iterations and subsets. So here I'm showing iteration 2, subset 16. And effectively that means here I've done 32 updates, because what happens is we still forward model as before, but look, you'll notice most of the forward model is empty. All I've done is forward project into just a tiny number of different azimuthal viewing angles in this forward modeled sinogram. So therefore, when I take my ratio, I only need to do the ratio on the parts that I forward modeled. And then you can see here, the back projection is now only back projecting a very limited number of angles that are in that subset. And so I'm already good to go to do my multiplicative update. Now here, of course, I've got to divide by the back projection of unit data for that subset to correctly normalize as well. So this is really core, and I think most of the time people are doing ordered subsets based EM implementations just to speed up the forward back projection computations. Quickly to show you what that would look like for real data before I just touch on MapEM regularization in more detail. Showing you ordinary subsets EM with ordinary Poisson model, in other words, with the scatter and randoms background. What we'd have again is a uniform non-zero starting image. We would do, for example, PSF modeling for positron range. We do a forward projection. We do attenuation, normalization, add-on scatter, add-on randoms, and that gives us a model of the mean. We're taking a ratio of the measured prompt sinogram data to the model of the mean. We apply the adjoint to that ratio, and we'll do the back projection. We divide by the sensitivity image. That gives us a multiplicative correction, which we then use to multiply our image. And so the whole process goes on. And so, for example, here at 100 iterations, we've got a reconstruction of the FDG distribution. So just to touch on what would happen with real PET data. So to go more into the regularization then, the problem with that MLEM or OSEM or ordinary Poisson OSEM is that nearly always you need to terminate early to avoid overfitting the noise in the data. If you've got short time scans, it can be very noisy, or low radiation, low injected activity, you can have low counts. And so often we need to regularize. And so this is a very simple quadratic, this is like a Tikhonov regularization, if you like, that we could use for PET, where here we're just looking at differences between pixel values. And we're basically saying noisy images will have large differences, and so that gives rise to a large square, which is therefore a large energy, which means it's a low probability of image. So we're seeking image estimates that will deliver small values for this. And so we can see if the whole image were to be uniform, this would give us 0 energy. And so we're actually favoring those kinds of images. But obviously that's why, as Jakob was saying earlier, we need to trade off between our regularization prior and our data fidelity. And obviously we want to fulfill the data requirements and yet also fulfill the requirements of our prior knowledge that we're assuming about the image. And so that's why often there's a regularization hyperparameter like beta that is involved in the frontier, or alpha squared, I think it was, that Jakob was using. Okay, so let's see this in action for, this is just to go over in a bit more detail what we do in PET to use that quadratic difference prior, if you like. So what I'm showing first of all at the top here, just to understand where we're starting from, we have an initial uniform image, again, non-zero for PET, that's very important. We're doing an EM update. Normally, we just do a series of EM updates and get a reconstruction. Now with that map EM, what's happening is, and I'll show you a bit more in detail, we're doing a denoising of the current update, and then we're fusing it with that data-based update in the fusion block here, and then progressing forward. So what this is doing then is dealing with this log posterior. So you should be able to recognize that's the Poisson log likelihood to within a constant in that part there. And then with the posterior, what's happening is we have the likelihood multiplied by the probability of the image. And here we're saying the probability of the image was an exponential minus beta. Beta is the hyperparameter for regularization strength times some energy. And when we take the log of the likelihood times that prior probability, we end up with this log posterior, which you can view as like, if you like, a penalty on the maximum likelihood. So that's the data fidelity, and then that's the penalty function for that data fidelity. In other words, get close to the data, but don't get so close as to generate noisy images. And so the prior I'm looking at is this, in fact, it looks simple, but actually for PET, this is very difficult to implement and to get right mathematically. And that's why it took De Piero in 1995 to write a paper that managed to deal with this issue. Because the point is, we're saying that our next, the image X that maximizes this log posterior needs to have this penalty applied, where we're saying that the estimate, we're looking at differences between the pixels in our estimate that we're about to calculate. And so this turns out to be a very difficult optimization to perform, even though it's only a quadratic on a difference image. So when we go to the Poisson case compared to the least squares case, optimization generally becomes a lot more tough, as I hope you're beginning to realize. So let me show you what is done as a consequence of De Piero's work in 1995. What he did was basically use a surrogate function for this quadratic penalty. And I'll show you what it drops out to being in terms of day-to-day practice. First of all, then, reassuringly, we have a data-based update, which is exactly what I've just been graphically showing you. Forward project, ratio, back project, multiply. That's the bread and butter EM update that gets our image X to be in agreement with the measured data there. So that's part of the process. That's the EM update. And then the other part is based on this. Now, that is, if you like, it's like an energy, it's like an objective function in and of itself. You could just look at the data fidelity only, or you could look at the prior only. So this is, if you like, an energy surface that depends on the particular image that we're plugging in. It gives some energy measure. Now, if we're doing this surrogate-based approach, which is effectively what De Piero was doing, then what you get for an update is this very simple update formula here. So take a close look at this. We're saying, take your current image estimate xk, so that could be here. And then look, we're doing a neighborhood averaging. This is just like a convolution. Look at that, that's just a matrix W multiplied by X, okay? So these weights are saying how important the neighborhood differences are. So imagine that as some kind of, it could be a Gaussian kernel, something like that, that you might use in a convolution operation, for example. So what we're doing then is convolving, if, for example, that were to be like a convolution kernel, we're convolving the current image estimate xk. So that's this part here. But then the catch is, and in fact, this is what makes it work. You then have to add on the current image estimate xjk. So notice this update is xj, we've got xj there. This summation is just over the different neighborhood values within the current estimate, but then you just add on the current estimate. So it's like a kind of it's like a relaxed, it's like you smooth and then you add on the old image, and that gives you the overall denoised update that is, if you like, using this surrogate-like function for optimizing the actual function that we want to optimize. So quite involved theoretically, but what drops out is actually incredibly simple to work with. So database update, update based on fulfilling, minimizing that energy. Obviously you want to trade these two off, and that's where the fusion comes in, and where we now explicitly make use of the regularization hyperparameter beta. So the good thing about this overall fusion expression is that if you plug beta equals 0 in here, then obviously what you expect is just the MLEM algorithm. And if you put beta equals 0 in here, then that's exactly what you get. That term disappears, you're left with 1, 1, and this term here disappears as well. So we're just left with 2 divided by 2 gives the EM update, very reassuring. But with non-zero beta, then this gives effectively a fused update between the data fidelity and the smoothed update. Just to show then, and just to also explain, new is just this normalization factor. The sensitivity image S is just the back projection of unit data. And this is just your summation of your weights that make up your neighborhood averaging process, where you're requiring differences to be low in that weighted neighborhood. And I refer you to the neighborhood slide that I showed in my earlier presentation for that. So the kind of results that you'd get from that, unfortunately, I'm going to show it here for MR guidance. Sorry about getting ahead of myself. To explain, this W, not only can you use that like a Gaussian kernel that would say, okay, if things are far apart, then we'll allow them to be different, but if they're close, then differences matter. But you could also plug in MR guidance information here, and in which case, then you've got a sort of a spatially variant guided smoothing process, and that's what I'll be showing in the next slide, and also what you'll be covering next week in more detail. But as a special case in the next slide, I will be showing you where effectively I'm not using much MR guidance. So let me show you that. So first of all, here's the problem: a noisy MLEM reconstruction from only 5 minutes of floor better bend data, which is why we need to regularize. Now here, okay, so sorry, it is MR guided, so deal with that next week. For this week, this is a good enough approximation to using no MR guidance. You can see that it's done a lot of neighborhood averaging here. But of course, if you start building in MR guidance information, then you can begin to control how that smoothing is done according to similarities in the T1 weighted MR image. But I hope that's explained to you the foundations of MLEM, how we use OSEM to accelerate it, and how we can just do a denoising plus, if you like, a delay based on the current update for a quadratic neighborhood difference penalty, if you like, used in the De Piero method.